the second presentation in Unit 10 entitled How Much You Bench. It says contiguous effort, not strength or intelligence, is the key to unlocking our potential by Winston Churchill. So, first, what we know. We know that acid strength depends on the dissociation of hydronium ions, which we call H+. Sometimes we refer to them as protons, but really the correct name is a hydronium ion. We also know that complete dissociation refers to a strong acid, and you should have memorized the 7 strong acids. We also know that base strength depends on the dissociation of hydroxide ions. Okay, so hydroxide ions. We also should have memorized the 8 strong bases that we've learned in the previous presentation. So, the pH scale. The pH scale is the strength of acids. It quantifies it. The pH scale is a logarithmic scale, which means whenever you change from 0 to 1, you're not changing by 1 or by 2. Instead, you're changing by a factor of 10. So when we look at 0, that really means 10 to the 0. Whenever we look at 1, that really means 10 to the minus 1. When we look at 2, it means 10 to the minus 2. When we look at 10 to the third, it's really 10 to the minus 3, and so on and so on and so on. So you have a factor that's changing by a factor of 10, not by 1 when you change the pH. So this logarithmic scale allows for scale comparison. So we're normally not interested in a factor of 1 or 2. We're really interested in what's called a scale comparison, or a factor of 10. So here's how you measure acid strength. You have pH, which is what here, is equal to the negative log of the hydronium concentration. So whenever you do this, this is the strength of the acid. Most of the time we're going to be dealing with very small concentrations of H+. So when you do 1 times 10 to the minus second, you can take the negative log of that. Whenever you take the log of this number, remember the log is associated with the exponent number. It turns out that this is going to have a value of -2. That's where the negative comes into play, and you have -2, which gives us a +2. Okay, next it says the concentration of hydronium, and then the answer is increases the stronger the acid, because as you move down the scale to the pH of 0, what you're doing is you're changing the concentration from 1 times 10 to the minus 5th to 1 times 10 to the 0, which is just 1. So you're increasing as the pH drops. So as the concentration of hydronium increases, you have a stronger acid. Now it says a 0.4 molar solution of HCl has a pH of, so we start off by saying HCl. HCl is a strong acid, which means it disassociates completely. Which means if I had 0.4 molarity of HCl, I would have 0.4 molarity of the hydronium ion and 0.4 molarity of the chlorine ion. Now I'm not interested in the chlorine ion whenever I'm looking at the pH, but I am interested in the hydronium concentration. So because of that, I can say, okay, the pH is equal to the negative log of the hydrogen concentration, or the hydronium concentration. I say pH is equal to the negative log of 0.4. Whenever you do this in your calculator, it's kind of an interesting number. 0.4 is one of the only numbers that gives the exact same value as the log of that particular number. So whenever you do this, you actually get the same value of 0.4. Now that is a very odd occurrence. In fact, 0.4 is the only number that I can think of that actually does that. So please don't think that the negative log just cancels out and it's the same number. It only happens on this one particular circumstances. So next, it says H2SO4 has a pH of 0.25. What is the concentration of H2SO4 on the label of the bottle? So it says we are given the pH. We know that pH is equal to the negative log of the hydrogen concentration. So if we plug in 0.25, we have equals negative log of the hydronium concentration. So whenever you're doing this, you have to do what's called an anti-log. An anti-log means you take 10 and raise it to that particular value. Now, you don't really want to find the anti-log of the negative, so instead what I'm going to do before I take this is I'm going to multiply everything by -1. In other words, I'm going to take 10 to the negative 0.25 is going to equal 10 to the log of H+. Now the reason why I want to do this is because 10 to the exponent of a log, those are opposite functions. So this is like the same thing as taking 5 and multiplying it by 1/5. Okay, those are opposite functions, so because of that it cancels out. Or taking 2 and subtracting 2. Those are opposite functions, so they cancel out. Well, these cancel out as well, and they leave this H plus here. So now you have H plus is equal to 10 to the minus 0.25. And now this is something that you can put in your calculator. Whenever you put it in your calculator, you end up getting a value of about 0.56. Well, that right there is the concentration of the hydronium ions. But remember, we have H2SO4. Well, H2SO4 has 2 protons that disassociate. So because of that, we need to take that into consideration when we can consider what should be on the bottle. If I have 0.64 molar, remember that for every one of these that falls apart, I create 2 of these. So if I were to write this in dimensional analysis, you have 0.56, and then for every 2 of these, you have 1 H2SO4. So because of that, we actually need to divide our hydronium concentration in half whenever we write the concentration of the sulfuric acid, which ends up being 0.28 molarity, and then we should specify what it is, H2SO4. So a 0.28 molar solution of H2SO4 should have a pH of 0.25. Next, we have A has a pH of 3.6. How many hydronium ions are present in the 25 ml sample of the solution? So this is going to take it one step further. We're given the pH again, so we would say, okay, the pH is 3.6. What I'm going to do is I'm going to go ahead and say pH is equal to the negative log of the hydronium concentration. I'm going to plug in. I can say 3.6 equals negative log of H plus, and then I raise 10, and then I change the exponents. That cancels out, and I end up with a hydronium concentration of 10 to the minus 3.6. Well, when you put that in your calculator, you end up with a value of about 2.5 times 10 to the minus 4th. That right there is the molarity of hydronium ions. Okay, so we're on the right track. The only problem is I don't want to know the molarity of hydronium ions. I actually want to know how many there are. So what I need to do is I need to start and do some dimensional analysis. So I'm going to say I have 2.5 moles of hydronium ions for every 1 liter. Remember, that's the definition of molarity from Unit 9. So now that I have this, I can say, well, for every 1 mole of hydronium ions, that's 6.022 times 10 to the 23rd hydroniums. Okay, so if I were to stop right here, I would have the number of hydronium ions that are in 1 liter based on my concentration. The problem is I don't have 1 liter, so I need to take into account the sample. I have a 25 ml sample, so I'd say 1 liter is 1,000 mils, and then finally I'd multiply it by 25 milliliters. Milliliters cancels out, liters cancels out, and I'm left with just the number of hydronium ions. When you multiply 2.5 times Avogadro's number times 25, and then don't forget to divide by that 1,000, you end up with a pretty large number for about 3.8 times 10 to the 18th hydronium ions. Now notice how I didn't put brackets around it because it's not a concentration anymore. It is an actual number of hydronium ions. Next, we need to talk about the POH scale. So sometimes we actually quantify the strength of bases based on what's called a POH scale. The pH scale is basically the same thing as the pH scale. They're very, very similar. The only difference is instead of looking at hydroniums, we're going to be looking at hydroxides. It's the same logarithmic scale. It's based on, trying to look at different factors of 10. So you have the same formula. The only difference is OH versus OH. Okay, when you're looking at POH, you're looking at the negative log of the hydroxide concentration. So the concentration of hydronium, remember this is asking about H+, that trips people up, actually decreases the stronger the base. Okay, so the number of things that are acids go down, the stronger the base. Now, a lot of people will think of this in terms of hydroxide. Now, if it were hydroxide, it would increase as the stronger the base. So it says a 0.2 molar solution of KOH2 has a pOH of, this is kind of a trick question, you have KOH2. Remember, this KOH2 will dissociate into a Ca2 plus and 2 hydroxide ions. So because of that, if I have an original molarity of 0.2, this is going to be twice as much. So now I have a 0.4 molar solution of hydroxide ions. Because of that, I can now say, all right, the pOH is equal to the negative log of OH. When you do this, you end up with a value of negative log of 0.4, which is a number that we've already talked about. It's one of the only log numbers that's the same value. So it ends up being 0.4 is the pOH. Now, where would a 15.8 molar solution of sodium hydroxide fit on the, should say, pH scale? That's why it gives you this graphic. So where would it fit on the pH scale? And if you were to look right here, you can say, all right, well, I've got pOH is equal to the negative log of the hydroxide concentration. So we would say NaOH disassociates into an Na plus and an OH minus. So for every one of these, you produce one of these. As a result, we can say that the concentration of the hydroxide is 15.8. So when we take the pOH of this number, we take the negative log of 15.8, we end up getting a pretty large number, a pretty small number. You end up getting a value of about 1.2, which makes sense. 1.2, not 1.2 molar. So this makes sense because this is a pretty strong base. This is almost as strong a base as you can possibly have. But this question is asking me about the pH scale, and that's why you're given this graphic right here. And this is actually what we're going to get into in the next slide, but the pOH scale and the pH scale are related. So if you have a 14 on the pOH scale, that's a 0 on the pH scale. If you have a 0 on the pOH scale, that's a 14 on the pH scale. So what I'm going to do is I'm going to say, okay, well I have a pOH of 1.2, and that's going to put me right here. When I go down, it's going to put me right at about 12.8 as my pH. So the reason why we can relate the pH scale and the pOH scale together is based on the disassociation of water. You have a formula right here that relates the two together. The pH plus the pOH are equal to 14. Now the reason why they're equal to 14 is because water does a self-ionization. So every once in a while, water will become H plus and OH minus. Now that happens very rare. Water is generally a stable molecule, but it does happen. So whenever you do this, you end up writing what's called a K expression, just like we did in the last unit. You write a K expression. You can look at the hydronium ions, you can look at the OH minus ions, and then this simplifies where it does not include the water, because remember, water is a liquid and liquids don't go in these expressions. So now that equals 1 times 10 to the minus 14th. Well, for every one of these you produce one of these. This is kind of a review from the last unit. So because of that, you have 1 times 10 to the minus 14th equals x squared. Well, whenever you do this, you get a value of 1 times 10 to the minus 7th for each. 1 times 10 to the minus 14th, take the square root, you get 1 times 10 to the minus 7th. And that's the value for this x, that's the value for this x. So whenever you plug those in, you get a pH value of 7 and a pOH value of 7, which adds up to our original 14. That's the basis behind them equaling 14. So you do have the formula that pH plus pOH has to equal 14. So write an equation for the ionization of water. What is the pH and pOH of water? The equation that we have is H2O goes to H plus OH minus. Whenever you do that, you can say that the pH of water is 7 and the pOH of water is 7. Water is generally considered to be neutral. Now that assumes that it's pure water. The ionized water doesn't have other things dissolved in it, which can affect the pH. Now it says the acidity of a lemon is determined to be 1.4 using litmus paper. It says what is the pH? pOH. So we have pH plus pOH equals 14. So we would say, okay, the pH is 1.4. 1.4 plus pOH has to equal 14. I subtract 1.4 from both sides. And when you do that, you end up getting a value of about 12.6 is our pOH value. So if I ask you if something's acidic, something should have a low pH if it's acidic and a high pOH. Those go together. And our last example says, what is the pH of a solution containing 1.4 times 10 to the minus 10th molar hydroxide ions? This says classify the substance as an acid, a neutral, or a base. And so the first thing we need to do is we need to say, okay, well, I need to be able to find the pOH. So I would say the pOH is equal to the negative log of this particular substance right here, 1.4 times 10 to the minus 10th. When you do that, you actually end up getting a value of about, you can go from here and you can plug that value in. pH plus pOH is equal to 14. Okay, and when you do that, you can substitute this value directly in to the pOH number. So you can have pH is equal to, or excuse me, pH plus the negative log of 1.4 times 10 to the minus 10th has to equal 14. Whenever you solve for this, you end up getting the pH is equal to 14 plus the log of 1.4 times 10 to the minus 10th. You can put it in your calculator, or you could have put it in your calculator here, and when you do this you get a pH value of about 4.1. Because you get a value of about 4.1, that means that the substance is classified as an acid, as acids have a pH that is less than 7.